Welcome everyone. Uh, we'll be continuing our discussion on transformers, and then we will today look at some of the methods to train the neural networks. We have already looked at gradient descent, the vanilla gradient descent. I will extend the idea of vanilla gradient descent to the ones that are currently being used, and we will also look at some of the meta learning techniques such as transfer learning and distillation in this particular class. Okay, so before we move on to the learning algorithms, there was one little piece that was missed in the last class. See, if you go back to the architecture of transformers, we are looking at sequential data, right? We transitioned from the recurrent neural networks to transformers as an architecture, and we are looking at the sequential data. The idea of sequence, okay, which is a temporal ordinality, is embedded into a recurrent neural network through the parameter sharing and the hidden variable, state variable, right, that has a time transition to it. However, in a transformer, all of the data tokens in a sequence are processed in an independent manner. Okay, since there is no hidden vector, explicit hidden vector in the construction of the transformer as an architecture does not have the idea of ordinality of the input data. Do you understand what I mean? Suppose you have a sequence, consider a sequence you have a T-lin sequence. In an RNN, what happens is you have the hidden states. We start from x1 and x2, etc., and each of the input sequence has a different hidden state, and because of the temporal parameter sharing, these hidden states will embed the information that x2 succeeds x1 and so on, right? xt succeeds xt minus 1 and so on. Whereas in a transformer, so each of these tokens are fed or given as an input independently. There is no temporal ordering information that the transformer embeds. Okay, so to ensure that, or what do I mean by that? The transformer does not treat, or rather treats the first token exactly the same way as second token and third token and so on. So it does not know that the third token succeeds the second token and second token succeeds the first token and so on. So the temporal information is lost. So how do you do that is the question. Okay, so to incorporate the ordinality of the input sequence, another fixed time variable temporal variable needs to be accommodated or added into the system. So explicit time variable has to be added into the system. Okay, we'll have to say that first token comes first and second token comes later and so on, right? So we'll have to do that. So how do you do this? The easiest way to do it is to have a time variable. Okay, so let's call it as small t. It is simply 0, 1, 2, 3, etc. So define new data x as, or xi at the ith token, as the ith token plus the ith time token, that is it. So this will tell you that the first token is, because it has that particular additional information into it. But the problem with this is xi, as we know, is typically in d dimensions, right? It's a d dimensional Euclidean space, which is a very high dimensional space. And if you add a scalar to it, okay, empirically it has been observed that this information will be totally ignored. Why? because in a 10,000 dimensional space, if you add one dimensional scalar, that one dimensional scalar will not be taken significantly by the network that is there. This will be ignored as a noisy point. I mean, if you are looking the data as an image, if you have a speck in the image, that would get ignored while processing. So that would happen if you add a scalar. Therefore, instead of adding a scalar, what should you do is that, so scalar t gets ignored, and therefore a fixed vector of dimension d needs to be considered. So we need a function, okay, f, or we need a function f that would take this scalar t and give you a t bar which is from r to rd. So we need a function of this sort where given a scalar t, it would give me a d-dimensional vector, okay, that would have the same information as that of scalar. How do you do that is the question. There are multiple ways to do this, okay. One way to do it is called, okay, and by the way, this thing, right, this function f is called positional embedding. Simply a d-dimensional vector that corresponds to the temporal ordinality. So now how do you convert? We know, I mean, oftentimes we do the other way around, right? We take data from a higher dimensionality and project it to a lower dimension. We have to do the other way around now. So how do you do that? There are multiple ways to do this. One way to do this is by using sines and cosines, cosine functions. So example for this is what is called as a sinusoidal embedding, where if t cap of okay, so let me just explain that and then write the math. So what is the basic idea here is as follows: construct sinusoids of different frequencies, okay. So now how do we do that? So let's say that we have one sinusoid like this and you have another sinusoid and multiple sinusoids of multiple frequencies, okay. So on, what we do is that we take capital D of them, you get capital D of them, and at every time t you sample from all these sinusoids. If you do that, you get a d-dimensional vector at all points in time, right? Do you see what I am saying? You take capital D, so not capital D, so d number of sinusoids, okay, where d is the dimensionality of the vector, the input vector, construct d sinusoids of different frequencies, okay, and sample capital T of them. So you get capital T number of d-dimensional vectors, and each of these correspond to a time instant. Do you see this? This is t equal to 0, you sample, at t equal to 1 you sample, and so on, and you sample up to t equal to capital T, okay. And how many sinusoids will we have? Yeah, small d number of sinusoids is what we have. This is the idea, that is it. I will write the math for it. This is called sinusoidal positional embeddings, okay. So now we will write that. So if you take, so it is done differently for the odd times and even times, okay. So this is I comma 2t, we have sine I divided by some large number n to the power of 2t comma t, see I comma 2t plus 1 is cosine of the same thing. This is it. So you get a you get capital T number of d-dimensional vectors, okay. You add them. So now what happens? The same thing, right? So you replace x cap of I as xi plus t cap of I, that is it. So now the input has this ordinal information, right, the temporal information. which is being explicitly fed into the model right now. Does that work? Okay. This is about positional embeddings, and whatever we, yeah, question.
Since sine and cosine are periodic functions, like won't T be same at different intervals?
You take different frequencies, right? The reasons you take different frequencies along every D is for the precise reason.
But at LCM of frequencies, different is
No, you take sine and cosines in such a way that they are not the same. Even if they are same, all D values will not be same, right? You need a unique vector, that's it. Yeah? You take different frequencies to avoid the precise thing that you said. The question is, if you take sine and cosines because they are periodic, won't they get the same value? Because you, just to avoid that, you will have different frequencies that are being taken. Okay, right. Okay. And another point to be made is, whatever attention mechanism that we saw the last class, right, it is typically referred to as the self attention. Okay, there is another idea which is called cross attention, where if you have two neural networks, one which is called the encoder neural network, the other is called decoder neural network. We'll talk about it in a while. Okay, when we talk about autoencoders later in the course, in the context of unsupervised learning, I'll revisit this and talk about the encoder decoder models. But suppose you remember, I think I had mentioned about encoder decoder in the context of machine translation, right? There is an encoder. Most of the models today that we have, the LLMs, are decoder only models, which only compute self attention. Basically, the idea of cross attention is, suppose you have two neural networks, okay, or two functions. You compute the query from one neural network, and you compute the value and key from the embeddings of another neural network, and then compute attention. That's called cross attention. Get it right? So you take different embeddings coming from two different neural networks. You can, I mean, it need not be encoder decoder at all. It can be any two neural networks, right? So you take one of the, you have three projections that we need to compute attention. One of the projections you compute from one embeddings of one of the neural networks. The other two you compute from the embeddings of other neural network, and then compute attention. And this thing is called cross attention. Okay, just had to mention this for the sake of completeness. Okay, let's now switch gears and move to the topic of adaptive learning rate, learning from adaptive learning rate. Okay, so training. Okay, so pardon my back and forth. So let's do the other topics first and then get to the adaptive learning rate, because this is all encompassing. The adaptive learning rate will be used for training all kinds of neural networks. Let's do transfer learning, and then we will talk about distillation, and finally we will go to adaptive learning rate. Okay, so let me introduce you to this idea called transfer learning. We will stop here and continue in the next lecture.